Hello everyone, welcome back to the channel. If you're new here, I'm Simona and we break down complex analytical techniques into digestible practical knowledge you can actually use at the bench. Today we are tackling something that causes more confusion than it should. Headspace GC-FID calculation. Now I know what you're thinking. Oh great, more math. But stick with me. Understanding these three calculation methods will literally transform how you approach volatile compound analysis. Plus, I promise to make this as painless as possible. Picture this. You've got a sealed vial with your sample at the bottom and empty space, the head space at the top. You heat it up and boom, your volatile compounds start partitioning between the sample phase and the gas phase above it. We then sample that gas phase and analyze it with our trusty GC-FID. But here's the million-dollar question. We are only measuring what's in the gas phase. So how do we calculate the concentration in the original phase? That's where a three calculation method comes in each. Each one has its strength, weaknesses, and perfect use cases. Let's break them down. First up is the external standard method or ESTD for short. This is your bread and butter, high throughput workhorse. If you're running dozens of samples a day, this is probably your go-to method. The concept is beautifully simple. You prepare a series of calibration standard, usually 5 to 6, at different known concentration. You run them through your GC-FID, plot the response versus the concentration, and you get your calibration curve. Let's walk through this step by step. So step 1 is prepare your standard in a blank version of your sample matrix. This is crucial. If you're measuring ethanol and blood, you need to prepare your standards in ethanol-free blood, not in water or saline. Step 2. Analyze each standard under identical headspace condition, that is same temperature, same equilibration time and same everything. Step 3 is plot your peak area or peak height on the y-axis against the known concentration on the x-axis. You should get a nice linear relationship. The software calculates your slope and you're good to go. Now when you analyze an unknown sample, you simply read its detector response, plug it into your equation and calculate it. Now the concentration in sample is equal to the response in sample divided the slope. Easy, right? This is why labs love this method. It's fast, it's straightforward, and if you're running quality control samples all day, it's incredibly efficient. Now this external standard addition method can be done in solvent based or matrix based. Matrix based is preferred because there is identical partition coefficient. But if your sample matrix changes even slightly, maybe one batch has more salt, another has different pH, or there's varying fat content, your K value, that is your partition coefficient, changes and your results become unreliable. So what do we do when we can't perfectly match the matrix? Or worse, when we don't even have a blank matrix? That brings us to method number 2. That is the standard addition. Now the standard addition method or SA is honestly one of the most elegant solutions in analytical chemistry. When I first learned this technique, it completely changed how I thought about calibration. Here's the genius of it. Instead of trying to create a blank matrix that matches your sample, you use the sample itself as the matrix for your calibration. Let me show you exactly how this works. So in step 1, You take your unknown sample and divide it into 4 or 5 identical aliquots. Exact same volume, exact same everything. Leave one aliquot as is. This is your unspiked control. In step 3, to the other aliquots, add increasing precisely known amount of your pure analytical standard. So maybe you add 10 micrograms to one, 20 to the next, 30 to the next, and so on. Now, here's why this is brilliant. Every single vial has exactly the same metrics because they all came from the same original sample. The only thing that changes is the amount of analyte. This completely eliminates the matrix effects. So you analyze all these vials and you plot GC response on the y-axis against the concentration you added on the x-axis. You'll get a linear relationship, but here's where the magic happens. You extrapolate that line backwards past the y-axis until it crosses the x-axis. That x-intercept represents the concentration that would theoretically give you zero response. The absolute value of that x-intercept is your original sample concentration. You've just determined the analyte concentration without ever needing a black matrix. Beautiful, right? Now, if you want the absolute gold standard for precision and accuracy, especially in regulated environments like pharmaceutical lab or forensics, you need to know about the internal standard method or ISTD method. While standard addition solves the matrix problem, ISTD goes even further. It corrects for matrix effect plus that plague to day-to-day analysis. That is variation in injection volume, slight detector drift, differences in sample preparation. Here's how it works. You select a compound, your internal standard that's chemically similar to your target analyte, but it's naturally not present in your sample. Maybe it's deuterated version like a structural isomer or a similar compound that elutes close to your analyte on the chromatograph. You then add the exact same known amount of this IS to absolutely every vial, every calibration standard, and every quality control, every unknown sample, no exceptions. Now, instead of measuring the absolute peak area, you measure the ratios. You calculate the ratio of your analyte peak area to your internal standard peak area for both your standards and your sample. That is, as you can see here, the response ratio is equal to the peak area of the analyte divided by the peak area of the IS. So the concentration ratio is equal to concentration of analyte divided by concentration of IS. So your calibration curve plots concentration ratio versus the response ratio. And here's the beauty. Since both the analyte and the internal standard experience the exact same condition, variation and matrix effect, they cancel out in the ratio. What you're left with is pure precision quantification. This is why regulatory agencies often require internal standard for critical measurements. Okay, so you might be wondering which method should I use? That's a great question. Let me give you a quick decision tree over here. So when to use the external standard? When you're running high volumes of similar samples, you can reliably prepare black matrix. Your matrix is consistent batch to batch and speed is your priority here. And when to use standard addition technique? When your matrix is complex or variable and you don't have any blank matrix available and you're analyzing diverse sample types, and for you accuracy matters more than throughput. Now, when you're going to use internal standard technique, when you need the highest precision, you can't compromise with it. You are in a regulated environment. You're fighting instrument variability when the method is worth the extra complexity. And there you have it. 3 powerful calculation methods for Headspace GC-FID analysis. Remember, choosing the right calculation method is just as important as optimizing your oven temperature or selecting your column. Understanding when to use external standard or standard addition or internal standard addition will elevate your analytical game and give you confidence in your data. If this video helped demystify headspace calculation, smash that like button and subscribe for more analytical chemistry content. Drop a comment below and tell me which method do you use most in your lab. I'd love to hear about your experiences. Thanks for watching and I'll see you in the next video.